Perfect. So last, well, we started off with oscillation, and we saw with a bit of a demonstration of how we can really derive this wave-like feature of any sort of simple harmonic motion oscillation. So we saw is when we model any sort of circular motion, such as this one, and we try to take a shadow of this movement of this bob that is going in a circular motion, and that shadow denoted by the blue bob, this moves in a certain way, that is, the displacement of this bob somehow denotes how a typical pendulum or a typical mass with spring moves with respect to time or theta. So over here, what you see is how a pendulum would move back and forth, left and right, in terms of its displacement versus the theta. So as we see initially from position 1, as it goes to um, a positive direction, let's classify this as positive, let's classify this as negative, and as it moves initially towards the positive direction, that is towards in this direction, what happens is its displacement is positive. So its displacement increases, and initially you have a high velocity. And over here, as the bob starts swinging towards the right, covers an increasing theta over here, and we see that the displacement keeps increasing but at a decreasing rate with respect to theta, right? And when we model all of the points, so from this position over here, that is a phase of pi by 2. Now, when it comes back to the initial position over here, right? So this is the point of pi by 2. So goes here, comes back, right? When it comes back, it has a displacement of 0. Fair enough. Now it moves to the negative direction. So we see a displacement in the negative direction. So that is how we model this entire curve. Fair enough. Now the point is that I understand all of these graphs of displacement with respect to, let's say, theta. And later on, I convert this theta into a time graph. What do we see in terms of a time graph? We see, well, there's displacement, but I converted the x-axis from theta to time. How did we do that in the previous class? We simply said, well, my theta keeps increasing with respect to time. That's what we say, right? That's what we say. And how do we follow that? Well, we know that omega is equals to del theta by del time. And if we make del theta the subject over here, what we find is omega times t gives me the theta covered by the oscillator or the bob. So this oscillating object is called an oscillator. We discussed in the first class. And as the oscillator keeps moving around, we say the theta covered by the oscillator keeps increasing with respect to time. So if I just had to give you a simple example, if this is my position 1, this is my position 2 of the bob, this is my position 3 of the bob, initially it has a theta of 0 covered. It goes to the max position. It goes and covers a theta of pi by 2, comes back, covers a theta of pi, then goes to position 3, covers a theta of 3 pi by 2, then comes back, covers a theta of 2 pi, and now goes again to the right direction. How much theta do you think this bob has covered now? This bob would have covered 2 pi plus pi by 2, whatever that value is, right? So it's going to be 5 pi by 2. So now it comes back to the initial position, that is the equilibrium position. So 5 pi by 2 plus pi by 2, it is going to be 3 pi. Okay, so what you see over here as the bob at the starting position, position 1, where my displacement is 0, right, equilibrium position, time I can say 0, it starts moving in the right direction, and I say, well, at the max position 2, it covers a pi by 2 theta. Okay, now as it keeps swinging around, we say the theta keeps increasing. That's what we say. That's how we describe the motion or the position in some sense. So by understanding how much theta the oscillator has covered, I understand at what position the oscillator is at the current time. And can I prove that to you guys? Yes, I can. You have the graph. And if you just look at the graph over here, if it is at, let's say, 2 pi position, what do you think the displacement of the bob is? It is at the equilibrium position, right? It is at the equilibrium position. If I say pi is the phase or is a theta covered by the oscillator, will you be able to tell me what the displacement of the bob is? Yes, it is simply at the equilibrium position. Can you tell me if it is, let's say, 3 pi by 2? Yes, you can tell me. Yes, you can tell me. Because at 3 pi by 2, it is simply the negative maxima or the extreme left position over here, position 3. So just by knowing at what phase, yeah, I will provide that. Oh, give me a moment. It was Monday. Copy. This is the link of the class for the last class, which was on Monday. Okay. Okay. So now what I'm trying to revisit with you guys is if I know the theta or the angle covered by any oscillator, I know at what displacement my oscillator is at the moment. So what am I flag posting right now? You're supposed to understand that if I know the theta covered by the oscillator, I know its displacement from the equilibrium position, left or right, that is positive or negative. Okay. So granted that has been established in your mind, and if you understand this graph, I want to ask you guys something very important, and that is very, very, very crucial so that you don't have any misconception. Okay. Now, when you have, let's say, a bob over here, okay, 1, 2, 3. I'm classifying left as negative, so follow me, and right as positive. Okay. I'll just use the same color. Oops. Great. Now, what I want to ask you guys is, can you tell me at position 3, what is the phase of my oscillator? At position 3, what is the phase of my oscillator? Yeah. Yeah, at position 3. So the theta over here, by the way, is 10 degrees. So I want to ask you guys, while my left direction is negative and positive direction is positive, that is right direction is positive, at position 3, where it is reaching the maximum height on the negative end, that is left side, what is the phase over here of the oscillator? That's what I'm asking you guys.
No, 10 degrees, no?
You're telling me 10 degrees? Yeah. So typically, this is the graph you have. So I'm asking you guys, what is the phase of the oscillator at the maximum end on the left side? That is position 3. Yeah. Are you saying 10 degrees? Any other answer? So I'm asking, what is the phase of the oscillator? So again, if I want to break it down even more, position 2 is the equilibrium position, and I You know what? I'll make your life a bit easier. I'll say this is position 1, this is position 2, and then finally this is position 4. Okay, so my bob starts over here at the equilibrium position. Okay, moves to the right hand side, right? Then comes back to the middle position. Okay, and now goes to the leftmost most side. Okay, so what is the phase of my oscillator at this position when it is at the leftmost position of the maxima on the left side? Give it one more try. It is,
30.
yeah, 30.
Mm-hmm.
Now, are you saying in terms of degrees?
Yes, 30 degrees.
30 degrees. Would you like to explain why 30 degrees? If not, that's fair enough as well. So, 30. Mm, okay. So, I mean, 30 in terms of pi was, in terms of radian, I was trying to think. But anyways, point is, no, not 10, not 30. No, none of that. So I guess why you're saying 30 years, you considered it went once here, 10 degrees, came back 10 degrees, and then went over here again 10 degrees. I believe that's the explanation behind your answer. Fair enough. Good consideration. And in terms of the theta covered with respect to this fixed position over here, yeah, technically you're right. But that is not the phase of my oscillator. No. So when I say the phase of the oscillator, what I mean is over here, when you draw, let's say, the displacement with respect to the phase of the oscillator, remember that at the maxima, what is the phase? Pi by 2. Remember when it's coming back to the equilibrium, what is the phase? Pi. And when it is at the negative maxima, what is this? Negative maxima. So negative maximum displacement, negative amplitude. What is this supposed to be? 3 pi by 2. And this, 2 pi. 0 again. So what I am trying to trick you guys with is saying, well, the theta being made with the ceiling, that is with the normal with respect to the ceiling, is 10 degrees. Fair enough. That is where the maxima is. Whenever my bob is making 10 degrees with the normal to the ceiling, that is where the maxima is. On either side, positive maxima, this is 10 degrees, right? And then we have the negative maxima, which is also 10 degrees. Okay. So when you tell me that the phase of the oscillator is 10 degrees at the negative maxima, that is not right. Yes, that is the theta covered with respect to the normal to the ceiling, sure. But that is not the phase of the oscillator. No. The phase of the oscillator at this position will simply be 3 pi by 2. Why? Because this is the negative maxima. Okay? I'll be clear on that. Don't get confused with what theta is being made over here. I tried to trick you guys with that, but what you guys should focus on is when I say the phase of the oscillator, that is at what position it is, that is with respect to its maxima, minima, and equilibrium position. Whenever it is at the maxima, you have a multiple of pi by 2. Okay? Whenever it is at, you know, the minima over here, I mean negative maxima, it is going to be a multiple of 3 pi by 2. And whenever it is at 0 or equilibrium position, it is a integer multiple of pi. Okay, remember last class I gave you guys another bit of example, or I tried explaining to you guys why always, where did I write that? In pi thing. Mhm. So what I was saying last class, that whenever you have a positive integer multiplied with pi, and this is your phase of the oscillator, this will always give you what? The equilibrium position. So if I say n pi is the phase of my oscillator, where n is an integer value, a whole number value, it will always remain in the equilibrium position. Why? What is the phase at position 1? 0. What is the phase at position 3? When it goes and comes back? Pi, right? Over here, it's pi. So 1 times pi. 1 is the whole number. When it comes back, it is 2 times pi. Again, the equilibrium position. This is the equilibrium position. So it goes from 4 to 3. So 3 over here is, sorry, 4 to 5. And there will be another position over here, 5. So over here, it's 2 pi. So again, you continue this graph, goes on forever. So next it will be 3 pi over here, right? And then it will be 4 pi over there, and so on and so forth till infinity. So whenever there's a positive integer value multiplied with pi, you know our oscillator is at the equilibrium position. That's something we all can be guaranteed about. Okay? Now, that is with respect to x being denoted as a is equals to sine omega t. Okay? Now, what would happen if it would be x is equals to a cos omega t? What happens then? Where do you think the maxima comes? At what degrees? Can someone tell me where the maxima is? So where I get the maximum displacement at what degrees in terms of radians or degree? Doesn't matter.
Pi.
Okay. Yeah. So one of the maxima, that is a negative maxima, is at pi. Okay. So this. So let's say, why do we use the cos one? That is with respect to an oscillation where your starting position is from the maxima. Okay. So when you have something like this, and this is your starting position, let's say this is 10 degrees with the normal, doesn't matter, this doesn't matter. But when your starting position is a maxima, notice the cos function, the starting position is a maxima. This is when we use the cos function. This is positive maxima. So when you're starting your oscillation with being at the maxima, you denote that oscillation with respect to a cos function. Because at 0 degrees, what is the displacement over here? 1. Okay. Granted, a is equals to 1, or there is no a. Granted, there is no a. Okay. Then yeah, displacement is 1. Because cos varies from 1, positive 1 to negative 1. So when do we use the cos function? When you have the oscillation starting from the maximum position. Do you need to know that? Yes, you need to know that. But will you be tested with this formula? Not much. You will be working with the sine function mostly. Now, again, so when do you see the maxima, or let's say the positive maxima? You see the positive maxima at, let's say, over here is 0 rad. Then you have negative maxima at pi rad. And then you have, this will be 2 pi. So what do you think happens over here? When do we get to see the, how would you denote in terms of n, in terms of cos theta functions, when do you get to see the maxima in terms of n? So for example, n pi, where n is a whole number, we always get to see a maxima in terms of the sine function. So if your x is denoted by this at n pi phase, doesn't matter what whole number n is, it will always give a phase, it will always give a displacement of maximum. Clear? So over here, when you see the sine function, sorry, it will always give you equilibrium position, not maximum. My bad, correction. Equilibrium. Okay, equilibrium. So whenever you have 0 pi, 1 pi, 2 pi, or 3 pi, 4 pi, 5 pi, all of these phases for the sine function, it is a equilibrium position or a zero displacement. Now, in case of my cos function, and by the way, in case of the maxima, when you get to see the maxima, pi by 2, okay? Pi by 2 plus pi. So this is one of the thing, this is one of the position. Next position would be pi plus pi by 2. This is where another positive maxima will come by. Then again, pi plus pi by 2. If you guys have done P1, you guys have seen how this goes on forever until unless there's a range given to you. So this is how you get the maxima for the positive end. And for the minimum end, that is the negative end, so it will be, this is one of the position, 3 pi by 2 is where you get the negative maxima. Then the other one will be pi plus 3 pi by 2, right? And then pi plus pi plus pi plus 3 pi by 2. So it goes on forever till infinity until unless a range is given to you. So now that's beyond the point. What I want to show to you guys is, well, let's say if I continue this graph, the cos one, so I've come back to the cos function. Okay, so this is pi by 2, no worries, pi, 2 pi. So I'm trying to denote where my maximas are. Okay, so this is 2 pi, and this is going to be 2 pi plus pi by 2, 2 pi plus pi by 2, 3 pi. This position is 3 pi, 3 pi plus pi by 2, then pi by 2, 4 pi. Okay. Now look, can you guys tell me in terms of n and pi, what positions in terms of an expression, for example, when I say at n pi phase, where n is a whole number, the displacement is 0. An expression like this, can you explain to me in terms of the cos function, at what positions do we always see a positive maxima? Can you guys give it a try? So I want from you guys, in terms of n and pi, at what positions do I always have a positive maxima? The answer is not n pi, it is something else. What do you think? So in terms of the cos function, yeah, go ahead.
N is an integer.
Did you say n is equals to 2?
I said N is an integer.
Yeah, n is an integer.
Would it be 2 and x2 and 5? All the
Perfect. Yeah. Perfect. Yes, that is exactly what it is. So what you're seeing over here, what you're following over here, every 2 multiple of pi, right? You have the maxima, the positive maxima, right? So I will define it a bit differently now. Okay. So now I have this expression. So I'm saying at every 2n pi phase, my displacement is max, where n starts from 0 and is every positive whole number value. Okay, so what can n be? N can be 0, n can be 1, n can be 2, n can be 3, and so on and so forth. And can we see this in this graph? Yes. When is n 0? If n is 0, what will my phase be? 0. So if n is 0, my phase is 0. If my n is 1, my phase is 2 pi. Do I have a maxima at 2 pi? Yes, I do. Yes, I do. What happens if my n is 2? 4 pi. 4 pi. Do I have a maxima at 4 pi? Yes, I do. You see the beauty of maths over here. So I have simplified everything into one expression that is 2n pi, and I added a bit of uh, definition of what n is, right? Defined what n is, and I expressed in this expression. This made my life a lot easier. So at every one of these positions, I have a maxima. Is this important? Sure, could be. They can give you trick questions. They can try and ask you to, give an expression for when the maxima is always seen or when the minima is always seen. Okay, but this is not exactly what the trick was. This is just something a bit extra that I wanted to cover with you guys. Okay, so that is one thing. Do you all understand, hopefully, how to express all the
It's
maximas or
when
minimas? Yeah,
n,
yeah,
so
go ahead.
it's when always an even number, is it?
For n, are you talking about n?
Yeah, yeah.
No, it could be anything. I showed you guys n could be starting from 0 to 1, 2, 3, 4, 5, and so on and so forth. It could be anything. Now, in my case, the example I was showing, that is maxima for a cos function. In that case, n can be anything. But let's say any other, let's say I'm talking about when is displacement always 0 in terms of a cos function, then it n could take different values. You could say, I mean, I don't know, you have to figure it out. So let's say if I just show you the example, right? So this is 0 and this is pi by 2, right? This is pi, this is 3 pi by 2. Oops, 3 pi by 2. And this is, well, 2 pi. Again, 2 pi plus pi by 2, 5 pi by 2, right? I'm on the right track, right? Yeah. Now, 3 pi, 3 pi plus pi by 2, 7 pi by 2. Okay, pretty long. 8 pi by 2, 4 pi. Okay. So same thing I've drawn again. Now, when do I have the equilibrium position? For example, let's work with that idea. Um, I have at half pi. So this is how you find the expression. So follow my thought process over here. So I have my equilibrium position for the cost function. This is displacement versus graph. So I have at half pi, then I have again 3 by 2 pi. When do I have it again? 5 by 2 pi. When do I have it again? 7 by 2 pi. And let's say I have 4 of these positions that I can work with. And can I distill something down from this? Well, yeah, sure, I can. What I see is it is half. So I see 1 plus, mm, so I see a difference of 2 at the numerator every single time. So I see, well, n could be 1, 2, 3, 4, 5, 6. What if I do that? 1, 2, and just add 1? No, that doesn't work. What if I have a difference? Yeah, 2, 2, 2. Yes, there's a difference of 2 at every one of these positions. So I could say that. So at every 1 plus n, okay, then 1 plus n by 2 pi pi is this part. So mhm. pi. Now next one, you can say half pi plus 3 pi. Okay, that took some time. So half pi, then half plus pi, then half pi 2 pi, then half plus 3 pi. How do you think I can denote this? I've basically distilled it down in terms of pi. What do you think is happening over here? How will you distill it down in terms of n? How do you think you will distill it down in terms of n? How can you express it now? Any idea? No? Any clue? If I had to express in terms of n, how would I express it now? Okay, I'll show this to you. So it starts off with, yeah, were you going to say something?
I was going to say maybe it's n over 2 pi.
N over 2 pi. N over 2 pi. Okay.
No, not
What
like
else did
that.
you say?
Um,
How then?
n pi over 2.
N pi over 2. N pi over 2. Okay. Okay, let's see. Let's see what I do. Now, what I was going to say is, let's see if it matches. So what I was going to say is, you will have half pi plus n pi. Okay. And what happens in this case? I describe n as ranging from 0 to infinity, where all values are positive whole numbers. Okay, that is what I say. So the basically n will go from 0 to 1 to 3 to 4, so on and so forth. Okay. Okay. Now, okay. So what happens when n is 0? Half pi. Okay. I give this half pi. What happens when n is 5 plus pi, which is 3 pi by 2, right? So now, what happens if I okay, am I audible again? My bad. It keeps happening. Okay. Perfect. Now, what I was saying is, so I can now explain that this phase is exactly where at every single position I have a equilibrium position, right? That is, we were finding the equilibrium position, right? If I'm not wrong. Yeah, equilibrium position. So at every one of these positions, I have the equilibrium position, or displacement is 0. Okay, so what did I do? I basically, towards the beginning, I was trying to fit in a bunch of normal case scenarios that didn't work in my head. So I went on and I broke the values down into two parts. One was half pi, which was the repeating part, and the other was pi, which was increasing at every instant. So it was going from 0 to pi to 1 pi to 2 pi to 3 pi. So I basically broke everything down into one common factor, and one factor, which was pi. So it was going from 0 pi to pi to 2 pi to 3 pi, so n pi. So over here, in this case, what I see is, yes, n is increasing from 0 to yeah, what I see is n is increasing from 0 to infinity as whole numbers or as positive integer values. So this is how we can express it. Well, you were pretty close. Not bad. Good try. So any confusion? Oh, we found the, at every single count, find either the equilibrium position, the maxima, positive maxima, or negative maxima. This is how you can break down a bunch of the points, and you can formulate such an expression. Clear? Any question? So this one was another example. Okay. Fair enough. Am I lagging? Hope not. Delete.
Just
Yeah.
sometime. Yeah.
Okay. Okay. So are you clear on that n part? How n varies? Yeah, even in this case, it went from 0 to infinity as whole numbers or positive integer values. Okay. Uh,
Sir, could I
is
take a
it,
screenshot? The parts we
yeah.
explained.
Which part? Which part? I guess I'm lagging. My internet is kind of screwed, I guess. Yeah. The previous part?
Yeah. So from which part did we, from where we started? Right. I can write it down.
Okay. Let me know when you're done.
Did you go up a bit?
So this I haven't explained everything yet. The confusion part. There's still a bit left. Okay. You're done?
Yeah.
Perfect. Now, the last thing I want to cover in this part, although I'm stretching it a bit too long, um, is erase a bunch of things. Last class, when we were talking, Owen, you asked a very good question that when I have this blue bob movement, is it the displacement on the x-axis only, or is it the displacement from here to here? Okay, this is something you asked. Do you remember it? So is it the displacement over here
Yeah.
on the x-axis, or is it the net displacement between these two positions? Remember asking this, or was it different? Was it exactly same or different?
Yeah. Yes.
Okay, perfect. So now, that's something I do cover in this SHM in pendulum 17.8. So if you watch the video, you'll see me covering it a bit over here. But since I'm not going to cover these two, 17.8 and 17.9, because these are extra parts that I've included. So I've provided the link if you can watch those two videos. But I will cover it over here a bit extensively because I feel like that's an important information for me to provide to you guys. So now that's a really good question, first thing. Second thing is there's nuance to it. What I said last class that you only consider the x-axis movement, that was right. But with a certain caveat to it. And I will prove that to you guys. Why what I said works and why it may not work. So it works because we work with small angles or small angular differences at the ceiling. And technically, yes, you do work with small angles only, which is why just noticing the difference in the x-axis, that is the x component of the movement, that is enough. I don't have to consider the y component movement because it's very little, which is why the net displacement between the bob is pretty much the same as the x-axis difference or the x component difference between the initial and maximum position. And I'll prove that to you guys with maths. No worries. You don't have to worry about that. So if I just show you guys, zoom in very, okay. This is, let's say, A and this is B. I'm telling you guys, A is the equilibrium position, okay? Initial position. And B is the maximum position, okay? B is the maximum position. And when does the maximum position come? When it is making a 10 degrees with the ceiling or the fixed point over here. Okay. Now look, whenever we work with angles, let's say less than 15 degrees, usually less than 15 degrees, that is over here at the ceiling. So we make the maximum position less than 15 degrees. So we don't push the bob further than, let's say, this position. Let's say this is 15. So we don't swing it beyond this point, usually, when we are monitoring simple harmonic motion, because we make a bunch of assumptions when we are working with SHM equations. Okay. So one of the limiting factors, we tend to swing it between 15, 10 degrees. What's the benefit? Why do we do that? Look at this. When I've shifted from A to B, that is let's say this is the maxima. Negative or positive doesn't matter over here. It's irrespective over here. I will color this part as white. What is the displacement between A and B, the white line or the red line? The red line has two components, one which is straight up vertical and one which is horizontal. Which one is the displacement between A and B, the white line or the red line?
The white line.
Perfect. The white line is the displacement. Now, if I had this, what do you think the dashed line is? What length does that denote? It's a bit circular in nature. What do you think this is?
The arc length.
Perfect. Perfect. This is the arc length. So all of these three lengths are actually related. Okay. And it's very interesting. So that dashed line is actually the arc length. Do you guys remember from circular motion? I told you guys we do something called small angle approximation. And when we work with small angles, my, whatever arc length is and the net displacement between these 2 points is pretty much the same thing. So yes, although the bob is traveling a greater distance than the net displacement, the white line, those two values in nature is pretty much equal. That is the first thing. Okay. So those two lengths in nature is pretty much equal. So as you just look at this, it's not too different or far off. That's one thing when you work with small angles. But the other thing that I want you guys to note is we don't even consider this white line, my friend. What do we consider? Usually the x component movement of the bob. Okay. So that is what we classify as displacement on the x-axis. What do I have over here on the y-axis? Displacement, right? From the equilibrium position. And we have, let's say, time over here or theta over here. Okay. So when I say displacement is max or displacement is 10 meters.
No, sir. So
Yeah.
displacement is not in the x-axis. I'm confused with it. Can you say again?
Yeah, I'm going to clarify that. Yes, when we say the displacement, we only consider the x-axis. We consider the movement in the x-axis, but it is the same as the displacement. That is what I'm going to prove to you guys. Okay, that is the proof. That the white line over here that you see is pretty much approximately equal to the red line. That is the little y component and the broad x component. Are you getting my point?
Yes.
Yeah. Yeah, so that is what I want to prove to you guys, that it is not different. It is pretty much equal when you're working with small angles, such as less than 15 degrees. That is what I want to prove to you guys. So that displacement in nature, due to this approximation, we can say that whatever the displacement is along the x-axis is the net displacement of the ball. It is all right for us to say that. Try made up of this little red line x component, right? So this entire triangle, if I move to over here, right? Notice what happens over here. Notice what happens. So just using over here, then over here, you can find out your by using simple geometry. Um, you can find that out by using 5 degrees over here. But it's not too complicated. So now when you have an angle of 5 degrees over here and the hypotenuse, which is this white length that you see. So that white length is what? That white length is the net displacement between A and B. And my red line, this is the y component of the red line and the x component of the red line. So the x component of the red line, I classify that as D. So what I want to prove to you guys is x and D is pretty much equal. Pretty much equal. That is what I want to prove. So D is simply the x component of the movement. So from A to B, whatever the distance is in x component, that is D. And x is the net displacement between A and B. That is what we are going to use to prove that x is approximately equal to D. Let's see how it works. So I find out using the sine rule that x is equals to 1.74, or specifically, this is my x. Now, when I find D, that is just the x component movement, what do I find? 1.73648, which is approximately equal to 1.74. So this is the proof that my net displacement x is pretty much equal to the difference in the y component d. So this red line over here, that is the x component difference. And when we compare the net displacement and just the difference in x-axis, they're equal, pretty much equal, approximately equal. When you're working with degrees, let's say 15 degrees and less. Okay, do we get the point? Do we understand what's happening over here? Yes. So this is why, yeah, perfect. So this is why we can make this approximation that our displacement is happening in the x-axis. This is not going to be a problem for you guys. Don't worry about it. This is not going to be a problem for you guys. They won't ask you anything along these lines, that what does displacement really mean? Is it in the x-axis, or is it the net displacement? They won't ask this. I was just clarifying the confusion. And the other thing is, going from equilibrium to the maximum displacement, you won't say that the phase of the oscillator is 10 degrees, even though the angle covered is 10 degrees. The phase of the oscillator will be pi by 2, or if it's in the negative end, then that means it went here, came back, and then went here. So this total will be 3 pi by 2. So the phase in this case, position 2 will be 3 pi by 2. So that's what I wanted to with you guys. Now, important, these are very important. Very, 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 very important. These are things you need to understand because the graphs do come in your paper extensively. Okay, extensively. So now, this is the model oscillation that we are going to be working with. So you have the ceiling over here, you have fixed point, I mean, the string is attached to this one point, and the bob is oscillating from 1 to 2 to 3 and back to 4. Pair, this is, yeah. Do you have any question?
No, so this part is not in the syllabus or the previous part is?
No. I mean, it's not about being in the syllabus. This is about clarifying the concept of what's happening. But what I was saying is, they won't ever ask you directly that what really mean over here. That is it in the x-axis only, or is it the net displacement between the two positions? They won't ever really ask. It's just something I am proving to you guys so that you understand what's happening in terms of the displacement. Okay. So it's not about, they won't ask you anything along those lines. I just try to clarify what displacement really means. That's it. And this is in your syllabus, and extensively, very important. The position graphs. Okay. Okay. So now, what is in your syllabus? You will have to draw graphs and you will have to work with graphs. What kind of graph? Acceleration against displacement and velocity against displacement. These two are the AVS X and VVS X. So versus displacement graphs. And there's also versus time graph that you will observe. So you can have graphs in with respect to time or with respect to displacement. Okay. So what you saw up top over here, this is displacement versus theta, okay, or angle. Okay. And this can be converted into displacement against time. We saw how the conversion happens in last class. So I also showed to you guys how would this look like if I converted this into a versus velocity versus time graph. It is a differentiation. And how does the graph change? There's a phase difference of 90 degrees. So basically, if well, if my displacement versus time graph was the sine curve, my velocity versus time graph will be a cos curve. So it gets differentiated, and now you have a cos curve. So what is the phase difference? 90 degrees. So every time you take a derivative of a trigonometric function, let's say sine, cos, the consecutive function that you get will have a phase difference of 90 degrees. So if you take a derivative of sine, it becomes cos. And if you take a derivative of cos, it becomes negative sine. And derivative of negative sine is negative cos. And so on and so forth you go, right? And each of these cases, you add a phase difference of 90 degrees, 90 degrees, 90 degrees. Okay? Basically, the graph shifts to the left. Graphs. Clear? So, yeah.
Could you repeat that? You were lagging.
So, in terms of, yeah. Oh, what's the last thing you heard?
Why they're separated by 90 degrees?
Okay, so when I have the displacement versus time graph, I have a sine function. Okay, so now when I take a derivative of this sine function, it becomes a cos function. So basically, it shifts to the left by 90 degrees. So, and now when I take of the cos function, what is it? Negative sine, right? So if I shift this again by 90 degrees, this is negative sine. See? So every single time you take a derivative of a trigonometric function, the consecutive function will have a phase difference of 90 degrees. So you go from sine, take a derivative, becomes a cos, take a derivative, becomes a minus sine, take a derivative, becomes a minus cos, take a derivative, becomes sine again. Yeah. So each of these cases, you have 90-degree phase difference. So sine and cos will have a 90-degree phase difference. Cos and minus sine will have a 90-degree phase difference. And minus sine and minus cos will have a 90-degree phase difference. Do we get the idea? So between these waves is a 90-degree phase difference.
Okay.
Got it?
Yes.
Left-hand side. Okay, this is how the velocity curve, the position or displacement, not displacement, acceleration with respect to the displacement or velocity with respect to displacement. So I'm on one axis, I have the acceleration, and on the other axis, I have the displacement. So usually what you have seen till now is time over here. Now you don't see time, you have displacement. So how do you work with this idea? Do we remember this equation? Yes. This is the important equation. This is what we need. So how do you think you would model this function as a graph? If my y axis is a, acceleration, and my x-axis is x, displacement, isn't it a linear relationship between y and x? Yes, it is. So it's going to be a linear function. That's the first thing I want you guys to understand, that it's a linear relationship between a and x. So acceleration and displacement, linearly dependent. And what is this? The gradient. And the gradient is negative over here. So you won't have a positive correlation, you'll have a negative correlation. Okay? So just by using y is equals to mx, we can plot this graph. And this is how acceleration versus displacement graph looks like. And if you're not convinced by maths, I will even prove it to you. One over here, I'm just randomly, arbitrarily saying 1, 2, and 3, not that it started over there. That is, that doesn't matter over here. So I'm just saying this side. So moving to the right is negative. If you notice the key over here, moving to the right is negative and moving to the left is positive. That's how I have defined it. Okay. So now when I am at position 1, what do you think happens? If you do an analysis of the force, is acceleration maximum over here? Any idea? Is acceleration maximum over here?
No.
Okay, where do you think the acceleration will be maximum?
At 2.
At 2. Where is velocity going to be maximum? 1, 2, or 3?
2.
At 1 or
Okay.
3.
Okay. So if my velocity is maximum at 2, at the same time, can my acceleration be also maximum? No. So
Acceleration is 0.
yeah,
No, max velocity acceleration is 0, right?
where?
No, I'm saying that maximum velocity acceleration is 0. Is it?
Right. So whenever my maximum velocity, I have an acceleration is 0. Right. Absolutely. So both are pretty much oppositely related. I don't remember what I showed to you guys. Yeah. So notice this. Whenever my displacement is 0, equilibrium position, right? Over here, this is the equilibrium position, 0. Okay. So if I just repeat some things, my displacement is 0 over here. My acceleration will be what? A is equals to minus omega square x. Displacement is 0. A will be 0 by pure maths. Okay. So that's one way to understand that at the equilibrium position, my acceleration is 0. What happens if I shift it to position 1? I have, let's say, a negative displacement because I have denoted right-hand side as negative. So yes, over here, my acceleration will be positive and maximum. Okay, because displacement will be negative. So let's say I have displaced it by 10 meters on the right-hand side. So minus 10 meters. So it will basically be A is equals to minus omega square times minus 10. So A is equals to 10 omega square. Okay. So notice one thing, whenever my displacement is maximum, my acceleration is also maximum, simply in the opposite direction. That is it. That is it. My acceleration will also be maximum when my displacement is maximum. Why is that? This is the maths talking. This is the maths talking. What about physics? What about physics? Over here, what happens? This is, do we agree that there's a tension over here? Yes. And that tension compensates usually for the mg. So in the rest position, we know whenever my bob is resting down, no movement left or right, no movement left or right, the tension upwards equals my weight downwards. So T is equals to mg, right? And this will be in equilibrium position, correct? Okay, so tension is equals to mg. Same thing, even if my bob is at movement, but at position 2, same as a typical equilibrium position, my tension exactly equals mg. Okay, my tension exactly equals mg. Exactly equal. And there's no unbalanced force over here. What that means is there's no net force over here. What that means is there's no acceleration over here. So at position 2, or the equilibrium position, what happens? Zero acceleration. Okay. But why is there acceleration at position 1 and 3? Okay, I'll do that as well. There's a there are two forces at position 3. One is the tension, that is by the string or whatever you have over there, and you have the weight, mg, right? These two forces, nothing else. So let's break this mg down into two components. Let's say this is going to be theta as well, okay? Because I'm drawing a line parallel to the string. So this is going to be mg cos theta, and there's going to be another perpendicular over here, which is mg sine theta. Now, does the bob move up and down over here? So does the bob move zigzag over here up and down with respect to the string? No, it doesn't. The bob only moves sideways. It doesn't move up and down. So is there any unbalanced force up and down with respect to the string or parallel to the string? Nope. No unbalanced force over there. Hence, T exactly equals to mg cos of theta. Exactly equal. That is in the y component, exactly equal. But where is the unbalanced force? Mg sine theta. And this is the direction of your acceleration. This is why you have maximum acceleration. Okay. Now, there are other things as well in terms of theta. You have mg sine theta, right? And as you increase this theta, as you keep increasing the theta, what happens? As you keep increasing the theta, the sine theta value keep increasing, right? So hence, that is why acceleration is also maximum over here. So there are multiple ways to explain this. There's so many ways to prove this and talk about this. And it's very interesting. But point is, what I'm trying to prove to you guys, at this position, there will be a acceleration because there's a net force. What is the net force? Mg sine theta. Simple, very simple. Okay, so the same thing happens when this bob is over here. This is mg, and there will be a string, and there's going to be mg cos theta over here, cos theta, and over here there will be mg sine theta. Now notice that the mg sine theta direction has changed, opposite direction. Okay, so over here, the direction is different, and over here the acceleration value will be negative because it's pointing in the rightwards direction. So over here it's negative. So notice that the direction of acceleration has changed. A, B, the acceleration is maximum at the extreme positions, that is 1 and 3. Clear? So what do we have? If I try to draw this at position 1, what happens? This is position 1, friends. My displacement is what? Positive or negative with respect to the arrows? Fast, guess. Is my displacement positive or negative?
Negative.
Perfect. A is equals to minus omega squared x. Let's say this displacement is 10 meters and it is a negative 10 meters. And this will be positive 10 meters. So A will be minus omega squared minus 10. Hence, yes, 10 omega squared. So acceleration will be over here positive, a positive value. So acceleration is on the y-axis and displacement is what? Negative over here, minus 10. Okay, so this value would be minus 10. Clear? Yeah, go ahead.
This is because we're considering acceleration positive, right? From left to right, that's why.
Yeah, so basically I just created this key towards the beginning of the sum that I'm considering right hand side as negative. So this works for anything. Acceleration pointing the right will be negative. Displacement pointing in the right direction, negative. So anything pointing in the right direction or in the right direction will be a negative quantity, regardless if it's acceleration of or velocity.
Doesn't, for example, if I say that displacement is negative when pointing towards the right. So we know
Okay, wait. Displacement is negative, but pointing towards right?
Yeah,
So displacement pointing towards right. Yeah, so this is what we have right now.
yeah. So then you said just now that we can take displacement and acceleration to be negative towards the right, but doesn't acceleration need to be opposite sign of
Yeah,
displacement?
acceleration is opposite. So wait, and I have the displacement over here. Is the displacement rightwards from the equilibrium or leftwards from the equilibrium?
Right words.
Rightwards from the equilibrium. So my displacement is negative. And when I drew the components, mg sine theta was directing in what direction? Left or right?
Left.
Left. Aren't both of those in the opposite? Yeah.
Oh, all right. Yeah.
Yes. So that's the thing. So my acceleration was pointing leftwards, and my displacement is right from the equilibrium. That's how we make that comparison. So that is why when your displacement is negative, your acceleration value is maximum and positive. Yeah. Okay. So now when this bob comes back to my equilibrium position, what do we know? Acceleration is 0 because my tension directly equals my mg. Okay, so that's at 0 over here, and then again same thing over here. So what happens over here? My acceleration is pointing right, it's negative. Maximum value is in the negative axis, negative y-axis, and the displacement is now in the leftwards direction, that is left of the equilibrium, hence positive. Okay, displacement is positive. So positive amplitude. A means amplitude, guys. A means amplitude over here. So the acceleration versus displacement curve. Okay, acceleration versus displacement curve. So what is maximum acceleration possible? My maximum acceleration possible is minus omega square a or omega square a. Okay, so this is in this is going to be pointing towards left. So in this position 3. position T, and this is position 1. So now, point is the maximum magnitude of acceleration that you can have is omega square A. How did we find that out? I can't change omega square, but I can change displacement, right? Displacement, and that gives me the maximum possible acceleration where x has been replaced by A, or where A is the maximum displacement, or x naught amplitude. So what happens when you have a velocity against displacement curve? Wow, this looks this is a circle. As extensively before. Wait a minute. Okay, so yeah, what do we have over here? Why does this look like a circle? Why does the velocity look like this? Well, there's a qualitative way to look at this, and a proof way or derivation way to look at this as well. Both I will show to you guys. Decent long. It's not in your syllabus. I'll move forward knowing that. What do you say? Yes or no? Give me a thumbs up if you want to know the derivation of this. I will qualitatively explain it to you, but yeah.
I think it's fine if you don't.
If you don't,
Yeah.
okay, fair enough. I mean, there's a video of this. I have talked about this 17.5. If you want to know extensively this derivation, it will take some time to explain this because it's a bit advanced over here. Okay. Yeah. I mean, it's decently possible to understand. If you just look at the video, you'll understand what it is, but it's not in your syllabus. Okay. So now, what is the velocity curve over here? When I have my pendulum moving left and right, what happens? By the way, I'm teaching with respect to the pendulum. It could also be spring and mass. It's the same thing in all cases. So now, what happens in position 1? Velocity is 0, right? So my since I've taken the right hand side as negative, right? So when I have the negative maximum amplitude, my displacement is, sorry, my velocity is 0. Okay. Is that not what we decided last class when we were talking? That every single time my bob reaches the maximum on either side, it momentarily pauses or instantaneously stops. Okay. So since that happens, because there's a change in direction, the pendulum initially moves in this direction, then changes its direction to this direction of movement. So since there's a change in direction, it directly stops. So can we be sure that at position 1, my velocity is 0? Yes. At position 1, velocity is 0 because it's the maximum displacement. Clear? And maximum displacement in the negative direction because I've classified rightwards as negative. Now, what happens at position 2? It's moving in what direction? Leftwards, right? And I know at position 2, the velocity is actually maximum. Why? Because this change in P, this entire change in potential energy, right? So whatever change in mgh happened over here, mgh converted to what? Kinetic energy. So this equilibrium position is actually the lowest position. Okay. So when you have the lowest position over here, all of that height, since height is maximum, all of that stored potential energy converts into kinetic energy. And if kinetic energy is maximum, velocity is maximum, right? So at position 2, what do we have? Maximum velocity. And is it positive or negative, guys? Tell me. It points leftwards. Positive or negative? This maximum velocity.
Positive.
Sorry. Positive.
Positive.
Perfect. So this is going to be positive because it's leftwards. So yes, at position 2, Vmax is seen. Okay. So I've plotted 2 points till now. This is 1 and this is 2. Clear? Let's go to another point. Position 3. Same thing as position 1. Maximum displacement, but now it's position 3, which is a positive displacement with respect to my key over here. Positive displacement. Hence, what is the velocity going to be over here? 0. Doesn't matter if displacement is positive or negative, it's a maximum position, hence my velocity will be 0. Why? It momentarily pauses. Clear? So at positive amplitude, I have my velocity being 0. Why? Coming back to the equilibrium position,
Sir,
what do I have? Yeah.
sir, but at negative maximum displacement, isn't the velocity also 0 at
Yeah,
1?
it is. Yeah. So it is 0 over here. Look. The velocity is the y-axis. Notice 0. Y-axis, notice 0. It has negative amplitude, and over here it has a positive amplitude. X-axis is the distance. Are we confused about the axis?
No.
Okay. Do we see what's happening over here?
Yes.
Perfect. So basically, in both cases, we have a 0 velocity. When you are at negative amplitude, which is this position, velocity is 0. When you're at the positive amplitude, which is this position, velocity is 0. And yeah, in the graph as well, it is 0 indeed. So if you just connect these two, where does it cut on the y-axis? And y-axis is my velocity. Okay, perfect. So now last one. Position 4 again. Equilibrium position. And what do you think happens over here? So in this case, which direction is the velocity? You guys tell me.
Towards the right.
Towards the right. Perfect. So since it's towards the right, the velocity will be negative. Okay. But maximum. Why maximum? Because it's at the lowest point or the equilibrium position. So it is
So we're
negative
saying that towards
equilibrium.
right, velocity is negative, displacement is also negative, right? Hello?
When yeah. Can you hear me?
Hello?
Yeah.
So you're lagging.
Okay. Wait. Hmm. What about now?
Yes.
Yeah. Now it's perfect. Yeah.
Yeah, I was asking, so we're considering displacement also negative towards the right,
Yeah.
as velocity, but
Yes.
acceleration is positive towards the right.
So when my acceleration points towards the right, it is negative.
But mustn't displacement and velocity be in the opposite?
Yes.
No, I
So
mean acceleration and displacement.
acceleration and displacement will be in the positive direction. Accurate. That's right. So let's say in position 1, what is the displacement?
It's negative.
Positive or negative?
Negative.
Negative. Okay. And the acceleration points in what direction? This is mg sine theta component. In what direction?
Yeah, it's towards positive.
Positive. Right. So this is not pointing in the right direction.
We
The
also need
acceleration,
to consider the mg cos theta.
the mg cos theta is exactly equal to the tension. So T is equals to mg cos theta. Okay.
Oh, all
So
right.
there's no unbalanced force over here. Yeah. So what you're saying is, I mean, yes, both are in opposite direction, right? But if, that basically means one points leftwards and one points rightwards. Okay. So at position 1, when I have the displacement towards the right of the equilibrium, it is a negative value. And when I have the acceleration at the same position, it simply points in the other direction, which is leftwards, right? The acceleration points leftwards. So now that is why the acceleration is positive and my displacement is negative. Not because they point in the same direction. Yes, they are different. No, they simply point in the different direction. My displacement is pointing or is in the rightwards direction, while my acceleration is pointing in the other direction, exactly other direction, which is why both are opposite signs. Okay, not because they're pointing in the same direction. Perfect. Are we clear on that?
Yeah.
Okay. So now, position 4, what happens? As you mentioned, it's moving towards the right. Hence, the value will be negative. And since it's the lowest position or the equilibrium position, the value or the magnitude of the velocity is maximum. So V max, but on the negative axis of the y-axis. Okay. So V max, but negative value.
You already sent the link for this class. I can't see it.
This one I will post today. It's already available in the playlist. That is chapter 17 or Oscillation by Science Stream. You'll find it. Um that is the proof of this is 17.5, video 17.5. You'll find it, but I will still link it for the convenience. So what is the equation then? How do I express velocity as a function of displacement? I know how to express acceleration with respect to displacement. That is a is equals to minus omega square x. But how do I express the velocity with respect to displacement? The simple answer is plus minus omega x naught square minus x square. And this will seem weird. Okay, it's a pretty weird and distinct equation. But since you don't want to see the derivation of it, or if you see the video, you will understand. You don't need to understand everything. You'll get some amount of understanding of how it looks like this or why it looks like this. I will recommend you guys watch that. Even if you don't understand it, even if you can't solve problems with that derivation, doesn't matter. Just understanding how it works will make sure that you remember this equation very easily. That's why it's better to look at derivations. Nonetheless, if I just still go on and qualitatively try to answer it, first of all, I'll describe what the variables are. What is omega? Angular frequency, okay, or angular velocity. What is x naught? Amplitude over here, right? And what is x? Displacement. So if I have position 1, 2, and 3, I'm telling you guys position 3 is maximum, is the maxima, and position 1 is the equilibrium position. And position 2 is basically a point where it's reaching position 3 or moving rightwards. And I'm classifying this as positive and this as negative. Okay. Now, in this case, let's say I want to find the velocity at position 2. Okay. I want to find the velocity at position 2. what do? I will first thing I want to know is what is the displacement at position 2, right? What is the displacement at position 2? So the displacement at position 2, let's say, is 5 meters. It's positive 5 meters. Okay. So when I plug in the values, I will say to find the velocity, I don't know the velocity, and let's say the omega or the angular velocity is 2 pi. Okay. And you have the x naught square, which is maximum displacement. Let's say the maximum displacement is 10 meters. So this is 10 meters and the position 2 is 5 meters from the equilibrium. So at the 10 meters, that is my x naught square. So 10 square minus whatever 5, I mean, position 2 is. So 5 square. So now it is simply putting it into the calculator. Okay. So root over 10 square minus 5 square, whatever the value comes, 100 minus 25, root 75. That is going to be your velocity. Okay. So the velocity will come out to be plus minus 2 pi root over 75. This is what the velocity is going to be. Fair? This is what the velocity is going to be. This is how you plug in the values. This is how you get the values from your question. That is the displacement, current displacement. That is, if I want to know what is the velocity at position 2, I take the current displacement and plug it into x over here. And I take the maximum displacement and plug it into x naught. And whatever the angular frequency is, that will remain constant, and I put it over there. So let's take some edge case scenarios. And I say, well, let's say x naught is equals to amplitude. I'm just saying that. Okay. It both mean the same thing. Both means the same thing. Okay. So let's say I want to know the velocity when my displacement is 0. That is at the equilibrium position. Agreed? I want to prove something to you guys. So I want to know the velocity at the equilibrium position or where displacement is 0. So displacement is 0. How do we work with the formula? V is equals to plus minus omega. Okay. So my x naught is a amplitude and my displacement is what? 0. At the equilibrium position, is there any displacement? Of course not. So what do you end up having? V is equals to plus minus a omega. Okay. So this is your maximum velocity. Remember, you guys just did this where when working with displacement versus time graph. You found out that max velocity can be expressed as a omega. Same thing when you're working with velocity versus displacement curve, you get the same thing. Velocity will be a omega. So maximum displacement times the angular frequency gives you the maximum velocity. Okay. So now, last edge case scenario. Let's say what happens if my x is equals to amplitude or maximum position. So in that case, basically this case, what will the velocity be? So I'm again proving something to you guys. So I take omega as whatever the angular frequency is, and x naught is a, and the current position is a as well. So a square minus a square is 0. So plus minus omega times root over 0 is 0. So velocity is 0. Okay. So I again prove it to you guys that at the maximum position over here or over here, it is 0 velocity. Great. Now, can anyone tell me why is it plus minus? Why is it plus minus? Why is the velocity plus minus? So I want to know that at position 2 what the velocity is. But why does this damn equation give me a plus and minus? Look at the graph as well. So I want to know what the velocity is inside this position when my displacement is 5 meters. Okay. Tell me, why is it plus minus? Why does the velocity give me plus minus? The equation. Why does it give me plus minus? Any idea? Nope. I'm not lagging, right? Oh, but can you guys hear me?
Yes, sir.
Okay. Okay. So now, why is it plus minus? Just to clarify over here, notice at 5 meters, it cuts the graph of the circle, the ellipse that you have in the graph at 2 positions. Okay. One is over here, the other is over here. Are both of these values positive? Absolutely not. One of the values are positive, that is on the positive axis. The other is on the negative axis. So when you have any displacement, it cuts at 2 positions of the ellipse. One will give you a positive value, the other will give you a negative value. Clear? So that is the math way of looking at it. What is the physics intuition of it? Why does it happen in the real world? I get the maths is giving me this, but does it make sense in the real world? Does it make sense to have a positive and negative velocity at each of these displacements? Yes, it does. You want the proof of it? I'll prove it to you. So when can the displacement be 5 meters or at position 2? What can the scenarios be such that my position is at position 2 or at 5 meters? A, the bob moves right to position 3. So the ball will be swinging rightwards with a what velocity? I described rightwards as positive. So with a positive velocity, it moves rightwards towards position 3 or the maxima. What is the other case? That my bob can have a position of 5 meters or displacement of 5 meters. Scenario B. It can also be that my bob is returning from position 3, that is swinging from the maxima to the equilibrium position. Got it? So it swings from the maxima to the minima, which is the equilibrium position. Even in this case, it can take position 2, that is displacement of 5 meters. Okay? Can it not? Obviously it can. It has to return home at some point, right? So even in this case, while returning, my velocity, my position can be of 5 meters or displacement of 5 meters. So the bob moves left to position, whatever I wrote over there, position 1. What will my velocity be? Negative, right? Because it is pointing leftwards. I classified leftwards as negative. So do we see the point over here? At position 2, at each of these position, here, 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 or here, 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 any of those displacements, there can be 2 possible velocities with the same magnitude, one positive and one negative, one while going there and one while returning from there. So that is why we have one one positive value and one negative value, regardless of what the displacement is. until and unless, of course, it is my NSA and positive rate, where the value will simply be 0, because 0 doesn't have positive or negative. Clear? So that is why we have two. That is why we have a plus and minus. Very important equation, this one. If you use Desmos calculator, something that we work with, and you plug in this expression, you will see an ellipse in front of your screen. Okay. So if you want to play around with the graph, you can do that as well. This is one question you should try. Note this down. 97243 October, November 2020. Give this a shot. If you have any question, let me know. You can post it on the classroom, no worries. Okay, try this. The other one you should try is this one. 97241 ON 2022. Which question? The oscillation question, question 3. Give this a shot as well. Okay, so you saw with respect to the pendulum how we can have these graphs, and now with respect to mass, you should work with the same idea. Same thing. So what I want you guys to do is see if you can apply the same equation with respect to the mass and spring system. So this is the derivation. You can take a screenshot if you wish, but you will see this in the video extensively covered as well. Till this point, we saw how the simple harmonic motion equation comes out to be. That is the acceleration equation. And we saw how the displacement versus time graph is achieved. That is from the displacement versus theta graph. After that, we saw the velocity versus time. After that, we covered some simple and common misconception. And after that, we covered acceleration versus displacement and velocity versus displacement. All of those graphs, very, very important. Next. This one, again, very important as well. What is this? This is basically energy graphs. So I told you guys before that there's a change between the kinetic energy and the potential energy of the bob as it shifts from one position to another. Okay, so there's a change or conversion of energy from 1 to 2 to 2 to 3 to 3 to 4. Okay, so that change in kinetic and potential energy we have to be able to plot in a graph. So how do we do that? We take the same example. I classify right as negative. Give me a moment. Yeah, so I classify right as negative as before and left as positive. Okay. Now what to do? What to do? What to do? If this is the case, how do I model the kinetic energy with respect to displacement and the potential energy with respect to displacement? Two things to do. Two things to do. I start off with the kinetic energy example. Okay, and let's see what happens. By the way, can energy be negative? Yes or no? Can my energy, any sort of energy, can be negative? Yeah.
No.
Yeah, no. Energy can never be negative, always positive because it's a scalar quantity. So it only has a magnitude. It has no direction. Okay, no direction attached to it. Great. So if I want to model the kinetic energy with respect to the displacement, how do we do it? Look at this. So I have position 1 over here. What happens in position 1? It is at the maximum position. And what do we know about the maximum position? It is going to have a 0 velocity. Okay. So if it has 0 velocity, kinetic energy will be 0. Kinetic energy will be 0. So notice position 1 is rightwards from the equilibrium. Hence it is negative displacement or negative amplitude.
So I mark this position as 0 because 0 kinetic energy. Where is kinetic energy maximum? Position 2 or 4, the equilibrium position. So when my displacement is 0, kinetic energy is maximum. Clear? So this is where velocity is maximum. Hence my kinetic energy is maximum. Okay. And my displacement is 0. What happens at position 3? This displacement is leftwards from the equilibrium, hence positive amplitude, but at the maxima on either side, negative or positive, the kinetic energy will be 0. Why? Velocity is 0. Okay, so velocity is 0, hence kinetic energy will be 0. Perfect. That's good. So now the other thing to clarify is my kinetic energy will never be negative, regardless of what's happening. Never negative. Okay. Kinetic energy in general is described by half mv squared. So whenever a velocity can be positive or negative, that you know, but regardless of that fact, the entire value will never be negative. Why? Because let's say velocity is negative, -2. If it gets squared, it is going to be 4. So can this ever truly be negative? Nope, not at all. Mass is never negative and half is half. So k can never be negative. So when I connect all of these three crosses, what do I have? I have a semicircle, half a circle. So this is how the kinetic energy graph looks like with respect to displacement. Clear? Clear? Okay. And can you prove this? Is this needed in your syllabus? Well, not really, but questions can come. They can give not a twist. This is something that they can ask you to derive and work with. So just understand this a bit. Okay. So what is the equation for the kinetic energy? Half mv squared. Anyways, it's not that difficult anyways. So half mv squared, right? This thing you know from way long before. What can I provide as my velocity? Do we know the velocity equation with respect to displacement? Yeah, we do. So we know two equations, velocity with respect to time. Do we remember the velocity equation with respect to time, guys? Velocity with respect to time is a omega cos omega t. Okay. And what is velocity with respect to displacement? By the way, why is this called with respect to time? This time over there. Time is the variable here. Time is the x-axis. Okay. So this is why this equation is called velocity with respect to time. So as time increases, velocity changes. What can increase over here? Time. So time is the variable. As time increases, my velocity changes. Okay, so it's a time dependent variable. Now, can I also express, why did I erase that? Can I also express velocity with respect to position? Yes, I can. So what would that be? That would simply be a omega cos, sorry, my bad, plus minus omega x naught square minus x square. Okay, this is the equation that we came across right over here. Okay. So this is the displacement, sorry, velocity equation with respect to displacement. Okay. So that is how we explain or identify or find out the velocity with respect to position. So there's one with respect to time. So I can vary the time and see the velocity. And I can also vary the displacement and see the velocity. There are two ways to go about it. Now, what else? Can I now plug in the velocity equation into my main equation over here. That is the kinetic energy equation. Yes, I can. I can do that. I can definitely do that. So which one do I plug in? Well, I'm trying to express this graph, right? So if I have kinetic energy versus displacement, we'll work with this. V is equals to plus minus omega times root over x naught square minus x square. What happens if I plug this in into my velocity? So the entire thing gets squared, so omega squared. So this plus minus, if it gets squared, it's only left with positive. So the negative shoes away, because plus squared is plus, negative squared is positive as well. So now what you're left with is half m times v squared. So this entire thing squared becomes omega squared times x naught square minus x square. Great. So this is what you're left with over here. Okay. So now, ultimately, if you just separate this in some manner, so I'm multiplying everything. So I'm opening all the bracket. So if you do this manually with pen and paper, so you separate this as this and this. You see something noticeable over here. What do you notice? The thing that you should notice is there's a part to this equation, this k equation, which is a constant, and one which is a variable. Okay, so this part, why is this a constant? Because none of these values can change with, let's say, a specific kind of pendulum in motion. None of these values can change. The mass of the pendulum can't change. The frequency, angular frequency cannot change. So the rate of change of angle cannot change. The displacement, the maximum displacement or the amplitude cannot change. Okay, so those things cannot change. But what can change is the current displacement. So the current position of the mass or the bob can change, or the oscillator can change indeed. Okay, so the displacement can change. The amplitude cannot, mass cannot, angular frequency cannot. So this becomes the constant. Okay, and this is the variable part of the equation. Now, over here, what happens when your displacement is 0? Notice very carefully. When your displacement is 0, this entire thing becomes 0. And you're left with this constant. And this, my friend, is the total energy of the particle. Or when you're at position 2, the maximum kinetic energy. The maximum kinetic energy, right? So over here at position 2 and 4, what happens? It is at the fastest pace or the maximum velocity. And this is your maximum kinetic energy. So when you increase the displacement or decrease the displacement, what happens? You shift towards this direction or this direction where the kinetic energy decreases. So you go towards position 3 or position 1. So what's happening is, as you increase this x from 0 to, let's say, 1 to 2 or 3, any value that you put in, it gets subtracted from this constant. Hence, the kinetic energy decreases as you move away from the equilibrium. Okay. So that's one thing to understand this part. This is the equation. Do you need to memorize this? No, not at all. If a question comes your way, you will be asked to derive this, most likely. Okay. So now, when it is at the middle position and this is 0, what does this look like? What will the k equation look like? Very simply, if x is 0, you're only left with this much, which is this. So this will look like this. I just take this half times m times omega times x naught whole square. So I've basically combined these two and taken the power of the whole expression. So what is omega times x naught? Omega times a, right? X naught is simply amplitude. Okay. And what do we know about a omega?
This is the maximum velocity. So half mv max squared, right? Isn't this the maximum kinetic energy? So when your velocity is maximum, your kinetic energy is maximum. Again, another way to prove it, that your kinetic energy is maximum when you're at the equilibrium position. So you can just prove so many things with a few data points given to you or a few expressions given to you. Now let's look at the potential energy one. Okay, let's look at the potential energy one. So let's say I consider the potential energy at this position 0. So this is my reference point. Okay, so PE at this point I consider to be 0. And as it increases in height, it gains what? mgh. It gains height. Okay, so the potential energy increases. And where does this energy come from? The kinetic energy. At this position, lowest position, where I consider the potential energy to be 0, I have maximum kinetic energy. And now as the bob moves rightwards or leftwards and it increases in height, it gains potential energy. It gains what? Potential energy. Okay, it has gained potential energy. Okay, so that kinetic energy now has transferred into potential energy. And at position 1, all of that kinetic energy, all of that maximum kinetic energy has converted into potential energy. Now at position 1, I have maximum potential energy. So if you model it on this graph, what you have at the equilibrium position, your potential energy is 0, right? Why is that? Because height is minimum or simply 0. If I take this as the reference point or the baseline, I consider my potential energy over here 0. Okay, and at the maximum point over here, A, where it has a certain height h, so it has a certain height h, I have gained some amount of potential energy. Great, I have gained some amount of potential energy. And where does that potential energy come from? The kinetic energy. So the kinetic energy transferred into potential energy. Will the potential energy ever be negative over here? No, it won't, because it's simply the energy value is simply magnitude. It is a scalar quantity, hence it's not going to be negative. Okay. So now at positive amplitude, I have maximum potential energy. Why? Because all of that kinetic energy was used up to increase the bob's height, this height. Okay. Now, at same thing happens at position 3, but at negative amplitude, or rather positive amplitude. So actually, this is position 3, right? So this is position 3, positive amplitude, and this position 1, negative amplitude. So this position 1 is this, and this position 3 is this. Okay. So when you're at position 1, you have negative amplitude, but maximum potential energy. And where you're at position 3, you're at positive amplitude and maximum potential energy. Okay, perfect. So those are the two cases. Now, okay. Now, last thing is I will try and join both of those. By the way, at position 3 and position 1, what is the potential energy? Can you tell me in terms of an expression? What is the potential energy of the oscillator, the bob? So I'm telling you all of the kinetic energy, whatever the maximum kinetic energy was, converted into potential energy at position 3 and 1. So all of the kinetic energy transferred into potential energy. What do you think that expression is? We just discussed when deriving over here. Yeah.
Kinetic energy is equals to potential energy.
Yes, so all of the kinetic energy has now transferred into potential energy. So specifically at position 3 and position 1, or let's say just position 3, what is this expression going to be of PE? What can I express this as? So for example, when talking about kinetic energy, I told you that this was the maximum kinetic energy, which was at this position, equilibrium. So I'm telling you, all of this kinetic energy, maximum kinetic energy, has now converted into potential energy. So how will you write the potential energy
Half m
expression?
omega squared x naught squared.
Perfect. So this is the expression of the potential energy at position 3. So at position 3, what will the energy of the particle be, or the potential energy of the particle be? This. Why? Because all of that maximum kinetic energy, whatever energy it had at position 2, which is half mv square, where v is maximum, converted into potential energy. So you could also say half m v max square. This is also right, because at position 3, all of that kinetic energy converted into potential energy. This entire thing converted to P at position 3 and 1. Now, if what happens if I join both of these graphs? So the PE graph and the kinetic energy graph, what happens then? It's very simple. What will happen is I will have both of the things adding up, and when you add both of these up, you have a straight line that is the orange one. So basically, you will be adding 0 over here plus, let's say, whatever the maximum value is over here, and this will result in the orange line. And then when you have, let's say, this red line, which is the midpoint, and the yellow value over there, so yellow is the potential energy and the red is the kinetic energy, right? And when I add these two, the sum becomes over here. And when I can do this for over here, where potential energy is 0, because at the equilibrium position, potential energy is 0, and at the equilibrium position, my kinetic energy is maximum. So when I add 0 plus the max, I get the point on the orange line. I do the same over here. So half plus half, you get the maximum. 0 plus the max, you get the point on the orange line. So when I add both the values, so KE plus PE at any given point, I get total energy of the bob. Clear? So whenever I add the kinetic energy individually at every position, the kinetic energy and potential energy, I get the total energy. And what is this total energy? If you ask me, this. Because this is the maximum energy possessed. For example, over here, when my potential energy is 0, kinetic energy is maximum. What is the total energy? Simply the kinetic energy. Total is the sum of KE plus PE at any given point. At any given point. So at the equilibrium position, when my kinetic energy is max and my PE is 0, what is the total energy? KE max. So this total energy stays constant through the journey, through moving left and right. So my total energy is simply whatever this is, or whatever this is. Okay? Simply that. Simply that. That is the total energy and remains constant through the journey. So last thing you have is 17.7. And damping. So two things pretty much going to take 45 minutes next class, and you would be done with the syllabus. So I would recommend you guys looking at 17.5, is it? Yeah. So I would recommend you guys looking at 3 videos. 17.5, 17.8, and 17.9. These are extra, but helps you with solving questions in the paper. And what are we left with? we are left with damping and energy graph against time. So energy vs time and damping. About gonna take 45 minutes and we move on to the next topic, most likely electromagnetism. Clear? So this is pretty much it. We have covered all of it almost. You can separately cover these 3 videos and you'll get the complete idea of the oscillation chapter and practice those 2 papers. This one, hopefully you've noted, and I'll give you in next class as well. I'll provide it. Is today they lagged out for some reason. Okay, just wait a minute. I'll give you the link. Share, copy. So today's class, you will have it available over here. Okay, so today's class will be available in this link. Fair enough. We're done for today. Next class, see you tomorrow, Sunday. Okay, any other question?
So where do I find these notes?
These notes, we won't be able to provide it right now, but we can simply ask you guys to, take a screenshot. Otherwise, I can wait till the end and provide it if that's okay to you. Like when we're done with all the things.
It's
Is
okay.
that fine? Yeah.
Mhm.
So I'll try, if you guys are sticking around till the very end, that is end of September, we can provide it to you guys. So whoever is sticking around till the very end, we'll reward you guys with the notes. Okay, so you'll get the entire black book. Okay.
Thank you, sir.
Okay, no worries. So that is it. Any other question?
No.
Great. So see you tomorrow. Best of luck. Bye bye. See you.